next in our series, Industrial Biotechnology Innovation Catalyst webinar. So for those of you that don't know, our IBIC project is a £5 million project funded by EPSRC to really leverage the fundamental science and engineering that we have done in and around industrial biotechnology in the University of Manchester, co-created with the University of Liverpool, and also pulling in our Northwest University ecosystem, including Salford University, Manchester Metropolitan, Bolton University, and also Liverpool John Moores University most recently. So very excited to be joined today by Tim and Andrew, co-founders of the company Imperagen. So Imperagen is one of the spin-out companies. Is it 2 years ago, 3 years ago? I'm losing track of time. That you spun the technology out and took the leap into creating a spin-out company. So really excited that we're going to hear a little bit more about what Imperagen is up to, doing, and a little bit more about its journey and where it's moving forward and looking forward in the coming few years. So without any further ado, I'm going to pass over to Andrew, I think, first, where we'll hear more about sort of the digital enzyme evolution. Over to you.
Do that. Okay, thank you, Aileen. Okay, can everyone see the slides?
Yep, can see them. Great.
Do that again, actually. Hang on 1 minute. I had this problem before.
Oh, it's okay. While you do that, I'll just remind everybody that we'll have a Q&A session at the end. But if you have got a question that you want to ask, or you find you forget before the end, if you're a bit like me, just please pop it in the chat and we'll pick up questions at the end. So yeah, feel free to pop comments, questions in the chat function as we move through.
Yeah, that's better.
Perfect.
Okay, yeah. Thank you to the IBIC team. Thank you, Aileen, Jennifer, Sabina, for invitation today. So, yeah, just quickly, myself, for those who don't already know us, perhaps from the University of Manchester Institute of Biotechnology, just introduce ourselves, and then we're going to cover again a couple of key aspects of our journey to developing a technology here at Imperagen and actually setting up the company. As Aileen hinted, it's been quite an exciting journey over the past couple of years since we incorporated. So, yeah, I'm Tim Eyes. I was originally a postdoc researcher at the University of Manchester Institute of Biotechnology, which is actually where the founding team met originally. Background in molecular biology and more lately enzymology. A lot of interest around how we evolve proteins, engineer enzymes in the laboratory, laying the foundations for the technology at Imperagen. So since incorporating and building the company, my role now is Chief Product Officer. So in principle, that's basically overseeing and managing all the sort of external customer enzyme projects and programs we run here, and general business development. Over to Andrew.
Yeah, hi, good afternoon, everyone. So I'm Andy Currin, so I'm with Tim, one of the other founders. And I used to work at the MIB and did a lot of my postdoctoral work there. And I'm Chief Scientific Officer for Imperagen, so kind of overseeing the development of the platform, the computation, and the robotics and the lab work, as well as overseeing the R&D projects as well. So I'm going to kick off with a bit of an introduction about who Imperagen are, what we do, why we do it, and then Tim, like I said, is going to give a bit of an overview of our journey so far and how we've come to the point where we are now. But yeah, I'll start with kind of like a bit of an overview of the technology, what we've been developing over the last couple of years, to give you a flavour for what Imperagen do. So as an introduction, I don't think I need to educate many people on this call about how enzymes are valuable and important molecules. Imperagen has a focus on developing enzymes for new industrial and commercial processes. So these kind of molecules, as everyone will know, are remarkable kind of nano machines able to create the vast kind of diversity of natural products that we see in the world around us. And most people will already be buying natural products as actual off the shelf in the shops. But they are very valuable molecules also for making pharmaceuticals and a large number of different manufacturing areas as well, which I'll come on to in a second. But just as an example, enzymes are already used in manufacturing, and particularly the example here is in making pharmaceuticals. So because of how selective they can be and how specific the molecules that can be produced, they are highly valuable catalysts for production of chiral molecules, and that's really valuable for pharmaceutical industry. So their level of stereoselectivity and the ability to produce enantiomer products is highly valuable, and they can also remove the need for extra synthesis steps, which are often implicated with alternative kind of more conventional synthetic chemistry routes, for instance, removing the need for using protecting groups, etc. So whilst they can perform some very valuable chemistry, they also come with some real strengths for sustainability. So very often they have great sustainability credentials. They are growable, that you can grow them with microbes, and also degradable, but also the reactions that they produce, that they work in, can be a lot less hazardous and a lot more sustainable, needing less solvents, etc. So they are very valuable molecules. The problem is very often that wild type enzymes are rarely ready to go, rarely ready for the commercial application. And even if they're pretty good, improvements are always desired to get the most out of that process. And the real remarkable thing about enzymes is that they can be engineered to improve their properties. So anything from getting better yields, new chemistry, can be engineered into the enzyme. And that is a fantastic feature of enzymes as catalysts as compared to other inorganic catalysts. Over? Thank you. So here is a brief summary on some of the areas where enzymes, and particularly engineered enzymes, are already being used. They are, as I say, already adopted, but we believe that there's a huge opportunity for a much wider adoption. And whilst they are very attractive as new processes, there are real major barriers that are stopping this wider adoption. And the key things here is that the process of engineering enzymes for a new commercial process is very often regarded as costly, time intensive, and also quite risky. It's hard to justify long timelines and expensive costs when you don't really know what you're going to get at the end. So why is this the case, really? In a nutshell, really, on the left is an example enzyme. It's an imine reductase, and what we've plotted here is every atom in this dimer molecule. So you can see the substrate and the NADPH cofactor bound in. You can see the complexity of this molecule, and actually for engineering, what you're trying to do is change the arrangement of these atoms in a way that actually gives you a particular performance improvement. And this image just gives you an idea of the complexity of the problem. Very commonly, working within making mutations in the active site is pretty well known and a go-to. This can get you some early improvements, but when you hit a brick, when you kind of max out here, where else do you go? And the challenge here is, how do you find mutations that are beneficial outside of the active site? And once you've found them, how can you quickly identify them in the lab and iterate the process as quickly as possible. So there are design and test challenges that really make the process very unpredictable. And one problem can compound another, really. If you have poor quality designs, it very often means you have to test a lot more. So actually you get into an ever increasing loop of exhaustive screening and high costs. These are challenges that Imperagen set out to try and address. So very briefly on this slide, we've looked to address challenges in the design of new enzymes, but also in the rapid testing of them in the lab. So we use our own algorithms to design where in the protein to mutate, and also moving that into the lab, testing these very rapidly with a fully integrated robotic platform. So the idea of using high quality designs with rapid lab testing, we believe, is really going to address some of the bottlenecks and the barriers to adoption of new enzymes. So this is a general overview of our platform, and what we've focused on doing is creating a highly integrated digital platform. So this is not just on the computation side, as you might imagine, but reaching that into the lab and having digitalization throughout the whole process has been a real grand challenge for us, but we believe it's going to bring real kind of benefits to the overall process. So everything in here is within our platform, and we've developed processes across all of these to help us run efficiently and quickly. So on the left, you can see we use a number of different algorithms to model and predict the properties of new enzymes, and very specifically variants and the chemistry that we're particularly looking at. We use large language models to feed in zero-shot predictions, and also we do the conventional kind of structural analysis of any kind of obvious places where you might want to mutate an enzyme. And we feed all this into our AI design process to design places in the enzyme that we want to go into the lab and test. We then use our own proprietary DNA design processes to design the experiments and go into the lab, where we run a fully integrated robotics process to rapidly test the variants that we've designed and feed back high quality data into the process. And the key thing is, once we've generated this high quality data, feeding it back into the AI model, I'll show an example in a minute, is a really powerful way of getting big performance leaps. So just to focus initially just on our computation element, as you can imagine, a digitalized platform is going to be very developed in its computational technology, and to coin a slight Americanism, having a full stack of computation tools is really essential. So everything here is integrated within our own custom-made web app user interface. We've brought all the technology together into a system that everyone in the company is using, from the comp team, the lab team. Everybody is working within this user interface to, starting on the left, run our simulation algorithms, run our LLM models, generate predictions, and take those predictions into a genetic design, over onto the right here, translating that into actual oligos for designing the mutants that we've very specifically designed, and then automatically designing all the robotics workflows and programs that we're going to go into the lab and test. And the bottom element here, although it doesn't have a fancy picture, is one of the real important elements of our stack, which is this data management. And that's the ability not just to capture metadata, but real experimental data within the system. And that becomes really important when we look to iterate the process and feed this data into AI. So actually having a LIMS system that can manage all this data, both in silico and experimental, is a really powerful capability. So moving from a set of computational designs, we really believe that the lab process of experimental testing in its current form, when we first spun out, was not conducive to really rapid testing and and quick turnaround of experimental data. So we've focused on developing our own unique workflows and methods that allow us to run end-to-end robotics process experiments with a very low level of user interaction. So actually, we can start now with a plate of oligos specifically designed from the AI designs. We load that onto the system. 7 days later, and with about 6 hours of hands-on time, the robot has run the whole process, and we've generated sequence activity data in 7 days, and that's dramatically faster than what we could do at the beginning of Imperagen and what others can do in other labs around the world. So yeah, this ability to generate sequence activity data in 7 days is really what we believe is going to transform the speed that we can move through our engineering rounds and deliver improvements. And the key thing is that all this is housed within our software infrastructure as well. So it's a fully integrated process that handles all of our data and metadata. So just to highlight some of the key benefits, the kind of the take-home messages of what the platform is delivering, we are finding that by using high-quality experiment designs, we can get a good high hit rate per round of improved variants. So we typically expect over half of all the variants that we screen in each round to have improved activity over the starting point. And we expect to have 100 to 200 improved variants of different sequences that are better than the starting point each round every time we do this process. And that really gives us confidence that our designs are of high quality, and we are going to have really good quality data to feed back into our models. We can turn experiments around quickly with our own processes, so 7 days on the robotics lab versus 30 days of what we would do conventionally with standard libraries. And the fact that we can generate high quality data and iterate this with AI guided models allows us and is showing in our data to give us very significant leaps in performance as we move through the iterations. And what we're aiming towards is not just to turn around a round of engineering more quickly, but to ultimately have to do less rounds before we achieve the objectives that we want for a project. So just to show a bit of data, this is a recent bit of data that we've had in the lab. We've just to highlight some work we've done on imine reductases. So they're very desirable enzymes in the pharmaceutical space for the production of chiral amines, from reducing imines to chiral amines. And we've been looking at an enzyme that is doing a very important reaction, but has a very low starting yield. And that's quite common for kind of an enzyme engineering campaign. You have an enzyme, it does the chemistry you want, it has a high EE, but yields are very low, and that is really stopping that enzyme from entering process development and scale up. So we did an initial round of our models, so our physics-based models and zero-shot predictions. So this is zero-shot essentially is predictions based on no prior data. You don't know, you've not looked at the enzyme before, you're making from scratch predictions on where you think the enzyme is going to be improved. And in this round, we got over 100, about 150 variants with 2 to 3-fold improvement in activity. And this is a really good starting data set that we then fed into our model and trained our model based on this data as well as our computation data. And it was this second round of libraries that was based on a trained AI model generating library predictions that really gave us this leap in activity that we were looking for. So actually in this second round, using the trained AI model, we got some really good yields. We actually got a high density of hits. As you can see on the right-hand side, a large number wasn't just a one-off hit, a large number of samples were giving over 60% conversion. And the best in this screen was an 85% conversion. So going from 4% conversion in 2 rounds up to 85% was a real validation of the process. And whilst it was a nice fold improvement to show it was improving, actually 85% yield is is really suitable to take that enzyme on for further process development and scale up. And that's really where we want it to be. We want it to be able to move the enzyme from suboptimal to process development as quickly as possible. So this is a recent bit of data that we were keen to be able to share. So just to finish up, we have a number of case studies, not just looking at yield, but different properties of enzymes. In the interest of time, I'm not going to go through each of these, but basically if people on the call are interested and would like to know more, then feel free to get in touch offline. Happy to talk through some more details of other properties that can be engineered using the platform, going from new substrates, novel chemistry, to improving yields at process conditions, improving enzyme stability, and also reducing cost of enzyme usage through switching of cofactors is all case studies that we've done in the last couple of years and we'll be happy to share. On that note, I hope that gives an overview of what we've been up to since we spun out from the MIB a couple of years ago. I'll hand over to Tim to get on.
Thank you, Andy. Yeah, so hopefully that's been a really useful introduction to the technology and the applications we've developed at Imperagen over the past couple of years, and where we're going to in terms of commercialization with partners in the pharma space and industrial biotechnology. But having touched on the science and our advancements, I was going to sort of take a step back a bit for the benefit of the audience on our journey from academia through to spinning out a successful TechBio company. Many in the audience are probably wondering, how did we get here and how did we end up being on this webinar today? And I think it'd be nice if I can hopefully inform and inspire some of the early career researchers on the call to our, from the story of our journey at the beginnings, our motivation, some of the useful lessons on the way, and what's in store for our future. But firstly, I think it's always good to start with, the motivation and really the sort of vision, the shared vision that we had at Imperagen. My background, like many of you, many of the researchers, scientists on the call, I'm originally a molecular biologist, and I did originally work in antibody therapeutics, so actually designing antibodies, building gene libraries, engineering antibodies to treat, very difficult to treat diseases like cancer. That was always what interested me from an early age, early career scientist point of view. But like again, many of you on the call, I think, and one of the main reasons for the start for IBIC forming was we're all very aware of the impending problems that climate change that we face with climate change. In terms of our society, our economy and our planet. I'm sure you're all familiar with this, these stripes for this figure of showing how the average temperature change over the past sort of 100 years or so. And it is quite disconcerting. It's not getting any better. And as we approach, the near future, where are things going? And shifting away from my initial interest in therapeutics, I was conscious that, what can biotechnology do to really help and address some of these, existential problems we have. And my interest really turned to enzymes and industrial biotechnology. As Andy's already, nicely introduced, and I won't go over it in too much detail, but enzymes are, nature's chemists, right? There's, thousands, millions of different enzymes out there, all carrying out critical functions amongst nature, which are potentially very useful to us in terms of a range of potential applications, from manufacturing to medicine to making food to cleaning our laundry. extremely selective because of their three-dimensional structure, and also essentially because they're natural proteins. They are biodegradable, and they can perform their clever chemistry in the very mild, more sustainable conditions without requirements of lots of energy or heat or hazardous solvents, for instance, at an industrial scale. And as we touched on, there's huge market opportunity for enzymes. They've been around in industrial biotechnology for, a number of decades, right? And are very successful as products and processes at the moment. But there's still vast untapped potential in enzyme technology. And one of the big challenges is really taking, as Andy's illustrated, taking an enzyme from nature, a starting point with very poor performance, to engineering it, changing that three-dimensional structure to something that can operate under more industrial or more applicable conditions. With that sort of scene set, let's just sort of wind it back a bit, back to the University of Manchester, where Andy was involved in the Synthetic Biology Centre. Spent a lot of his early career working on, new novel approaches to building smart gene libraries, principally for running directed evolution campaigns to improve enzyme performance. And published a great deal in that around that topic with his colleagues. He'd even not quite written the book on directed evolution, but edited it, which always makes me laugh a little bit. But it's we basically, Andy beginning to form and forge the early foundations of the technology that underpinned Imperagen, our ability to build these smart libraries. And he, through the university, filed the first patent for the generator method in 2018. And at that point, we'd actually known each other for a couple of years. We'd done our PhDs in parallel at the MIB, and we got talking, and I sort of pivoted away from my interest in antibodies and joined up with Andy again, while we looked to working with the UMIF, who's the University of Manchester's technology office, to explore basically sort of the commercial potential for this technology. And working with the UMIF, we established an industrial collaboration with a large enzyme supply company. So that was kind of like a ring-fenced 12-month project. I came on board, running the laboratory side of things, helping Andy sort of develop the technology a bit. And that was really, really successful. And at that point, we were beginning to wonder, do we have something that has, potentially commercial potential? There was certainly appetite from industry, who we were talking with and working with, but while we're still within the university, how could we explore commercializing this and exploiting it? And that led us to applying to iCure. Now, for those who don't know, iCure was a program set up by Innovate UK just over 10 years ago, and it's essentially a program that helps university researchers explore potential for commercialization of their technology while they're still in the university, right? Stands for Innovation to Commercialization of University Research. But in principle, what it teaches the early career research, if you like, is to go out there and explore the marketplace, ask questions, and see if there's an opportunity. And I put up this figure of what we call the valley of death, and this is the key point about iCure is basically, you've got a great, technology still within university, and you believe that there's a real commercial potential for it, and you can make money out of it. But actually, it's not that simple as just stepping out the door with your tech and getting investment and making money. You've got to get through loads of different pitfalls and obstructions to actually getting there. And unfortunately, most sort of early stage technology does end up in the valley of death. It doesn't quite make it to commercialization. And that's not usually down to the technology or the hardworking team behind it. It's often just not finding that right market fit at the as early stage as possible. So what iCure is designed to do is to really help these innovators and academics is establish, carefully explore the marketplace. Is there a problem? Does my technology solve it? And perhaps the most important point is, will the customer pay for it? And those are three key things. So please make note of those. Any interested enterprising people in the audience. So this is what really helped us kick things off. Essentially, iCure and Innovate UK buy out researchers' time for about a period of 3 months. So you get time out of the lab to go out into the wild, into the marketplace, and have as many basically meetings as you can across your marketplace of interest. Obviously, for us, it was the enzyme marketplace, which is massive and covers lots of different sectors. Discuss with customers, with suppliers, with competitors, the challenges and problems they face, and begin to validate your assumptions about your technology offering and what problem it's trying to solve, and therefore get an idea of the commercial potential. And then within iCure, it's not just the customer sort of validation journey. You get support, training, and feedback, and also access to sort of the next step in terms of funding. So for us, it went really well. It was a really amazing program for us that helped us get a much better understanding of the marketplace. I got out there into the wild, as I said, travelled between a year in the US, attending conferences, meetings across the marketplace, across loads of different sectors where enzymes are applied. We ultimately built a really strong partner network, which we still use today at Imperagen. And we had really good validation from the customers. There was real need for enzyme engineering. It's still a big bottleneck. A lot of companies were looking for problems to solve that. So iCure proved to be really, really valuable for us, and weren't very successful. We got through to sort of the next stage where we were ready to sort of incorporate and access some early stage funding. But then, so 2020, the pandemic hit, and we were kind of not quite full into the valley of death, but probably still stuck in research land at this stage. As I'm sure it's true for everyone during the pandemic, it was a moment for sort of pause and reflection onto where things are going next. And in the end, actually, that period of time was actually really useful to us. I was then successfully awarded an enterprise fellowship, which is run by the Royal Society of Edinburgh. So that's BBSRC funded program, basically for 12 months to supply further enterprise training. Of course, iCure, having done that customer discovery, was really useful in establishing the foundations of a kind of early stage business plan. We had traction. We just needed time to build out the plan. So that 12 months was really effective for us to do that. And again, the enterprise, through the enterprise fellowship, you get a lot of support and advice and training. And I'll just add, unfortunately, the RSC don't run the enterprise fellowship anymore, but the Royal Academy of Engineering do run something very, very similar. And are sort of available to sort of early career researchers with some with ideas and technology with commercial potential. So if there's anyone in the audience that's looking for that next step of help and support, I do recommend you look up at the RAE. Getting that time out of the lab to explore commercialization of your technology is really key. It's very hard to do, to juggle all these things at once. But during that time, we had established we've got this great technology, a lot of promise, and there was still a lot of validation from the customer community that they really want to speed up the process of directed evolution. And our technology we developed solved some of those challenges, but not all of them. And we were really, aware that we didn't quite have, although we could build these libraries to improve diversity and improve the efficiency of screening, we didn't really have the sort of clever, smart ways of very quickly zooming in onto the enzyme and determining which bits we should mutate, as Andy's kind of already alluded to. And at that point, on the back of my fellowship, we were led to speak to Andrew Almond, who is another lecturer based at the Manchester Institute of Biotechnology, who'd been working on a similar problem to us, like how do you speed up process of enzyme engineering, but from a purely computational point of view, basically using AI, smart chemical simulations to determine very quickly which bits of the enzyme are key to improving performance. And it's very, very obvious, very quick to realize that bringing these two bits of technology and approaches together, we're going to form a much stronger proposition for a company. And Andrew already started the process of patenting this technology. So the three of us got together, and that quickly led to us incorporating Imperagen using both these founding technologies. And we had a year or so still at the university to continue to develop the technology while we went through the spin-out process at the university, ultimately leading to the company incorporation. Now, again, Andrew Almond was sort of key to this because he's been through this process before, having set up a successful spin-out of C4X Discovery, which he spun out over around sort of 20 years ago now, and led that to IPO. And he was hunting around for another opportunity to do a spin out, and Imperagen was born. So with that, having set up and incorporated, we had the founding team, we had the IP in place, we set about looking to raise our capital, essentially, that was going to help us principally build the team, build the technology out, and get us that critical early stage customer traction. And we secured our seed investment from Northern Gritstone and IQ Capital of $3.5 million back in the summer of 22. So with that, the first thing was really building the most valuable asset, in fact, for any company is the team. So you've already heard from me and Andy, and I've introduced Andrew Almond as well. None of this really happens without the people. We built this amazing team of scientists at the science park here, tons of experience tackling all sorts of enzyme problems over the years. But another key thing is bringing in that commercial experience as well. So Rob Wilson, and now our CEO, joined us last year. And we have Peter Surfer-Vassethal, our chairman of the board. They both come from Codexis, which is the pioneer, California-based pioneer of enzyme engineering technology in the early noughties. So they've done a lot of commercial enzyme projects, and we're also supported by a really good advisory board with John and Frank covering different aspects of our technology. Next thing really was to build out the technology. Now, Andy, I was already introduced, the finer details of it, but in principle, I've inserted an embarrassing picture here. Of course, no talks complete without one. But yeah, we've come on a long way from, exiting the university on a trolley stacked with, cardboard boxes, moving over to the science park. There's even me there in a lab coat looking dangerous with a pipette. And over the past 18 months or so, turning that into our, amazing integrated platform, all the software, all the hard work behind all that. This slide probably doesn't do it justice, but the vision is now to commercialize this highly efficient, highly integrated enzyme engineering platform that can solve a range of enzyme challenges across different marketplaces. Okay, and so with that, we've built the technology, validated it on internal projects. We've run successful external projects with customers, and we've also brought in further Innovate awards, totaling over $500,000. Innovate have been particularly supportive of what we're doing. It's really great that we get support from these kind of networks and such things like IBIC too. It's been a great journey so far. We've done all sorts of different things, been invited to speak here and there. One highlight from last year was being invited by Innovate UK, along with Department for Science Innovation, Business Trade, on a trade mission to California to go and explore further the marketplace for enzymes and industrial biotechnology over there. It's in IBIC conference. So it's not just all work. There's a lot of travel, a lot of fun, a lot of meeting new people along the way. And just to sort of begin to wrap up quickly, I just thought I'd kind of throw this slide up just to sort of summarize the journey, so to speak. So a bit like, I suppose, engineering an enzyme the old way. So it's not a linear path really necessarily to go from the beginning to your final destination. The journey from academia to commercialization is definitely not without its challenges. It might look quite smooth from what I've just explained, but there's definitely some bumps in the road, and a bit of serendipity helps. The goal can seem a long way away sometimes, and kind of hard to reach, but plenty of pitfalls, and it is a bit like a snakes and ladders game. But what I would say, again, to any budding entrepreneurs out there, it's a long road, but it's very much a stepwise approach. Like there's 1,000 steps, right? And it might seem overall, when you're looking from the bottom, a long way, but you just take each of those steps at a time, and you will get there. And the key thing around that is basically having a good team around you to do that. I can't highlight enough how important having that team that we've built is key to getting us where we are today. And there's plenty of help out there too. There's plenty of good networks, organizations that can help you on your journey. Almost everyone I speak to on my journey so far, who work in academia or work in industry, are usually almost always happy to offer some, free advice in their time. Most people in business, it's not that cutthroat. It's, often quite friendly. People are always generally willing to help and advise along the way. Ultimately, we're all working for the same company, right? UK PLC or global PLC, if you like, and we do all have to take our training, our learning, our research, and turn it into something useful, and hopefully, improve the outlook for our society, economy, and planet with industrial biotechnology. So with that, I could have written an exhaustive list of all the people that had helped me, and us along the way, but I thought I'd just summarize it through icons and logos from the various companies and organizations that really helped us along the way so far, and hopefully there'll be many more to add along the way. And of course, IBIC are on there. We're very happy to be part of this budding network and looking forward to working more closely with IBIC and the other partners in the future. And just finally then, if you do want to get in touch, you're very welcome to. That's our sort of general contact email there. Happy to field any questions or queries from the audience that way. And I just wanted to note that Imperagen also been successful recently in securing funding for a secondment through IBIC. And there'll be a bit more information announced about that shortly, hopefully. But we are basically on the lookout for some enterprising researchers who would like to join us for a short period of time on a commercialization project. So it's not lab-based. It's actually going to be working on more of commercialization and business development aspects. So if there's any budding scientists on the call who are interested in dipping their toe outside of the lab into business development, please get in touch with either myself or IBIC, and that should be coming online pretty soon. Okay, I'm conscious of time. So with that, I thank again the IBIC and the audience for listening. Probably got a bit of time for a couple of questions.
Yeah, that's brilliant. Thanks very much, Tim and Andy as well. And it's great to see the journey, and it's great to hear sort of your realistic interpretation of that. Not realistic interpretation, but realistic discussion around the journey. But seeing overall that it's worthwhile, and seeing your trajectory being a hockey stick, which is amazing. Great inspiration. So we've got a couple of questions in the chat, and if you've got anything else you want to ask, just either stick your hand up or pop it in the chat and we'll come to you. So there's a question from Chris. He's wondering, can you pre-screen evolve recyclability, multi-cycle industrial application for usage over multiple reaction cycles?
Yes, I'll do that one. Do you know the chat? You just so.
Do you want me to repeat? Do you want me to ask again?
Yeah, just.
So he's looking at sort of pre-screen or evolve on recyclability and sort of the multi-cycle industrial application for usage in multiple reaction cycles. And he was also asking, can you factor in immobilization on solid substrates? Like
yeah, so kind of talking about polymer recycling, but it sounds a bit. Yeah, obviously we, a very kind of broad answer instead of getting into the technical aspects of it. So obviously the marketplace and opportunity for enzymes is very large, and more interested in polymer degradation and revalorization around that. So our beachhead really was looking at pharma API, so more smaller but complex compounds, and improving enzymes for that. And we've also run some, projects around, more valuable commodity chemicals as well. Mm-hmm. Saying that, in principle, our technology has been developed to be kind of as agnostic across enzyme classes, across chemistries as possible. And yes, we've been asked to look at, more complex polymeric substrates. So for the computational side of things, yes, we can run simulations of enzymes interacting with these polymers. And of course, we can predict, identify potential hotspots are there and build libraries. I think, as you say, that we've spoken to, users of this kind of technology in the marketplace, and the big challenge is, yes, more around the bespoke screens and technology you need for identifying whether the enzyme is broken down out of solid substrate. So in principle, yes, we can have a look at those challenges computationally, but we're aware and conscious that there are some challenges more on the actual sort of screening side of things. But yeah, Chris, happy to have a follow-up conversation if you want to get in touch after the call.
And in terms of the
Sounds
immobilization question, it's the properties that you'd need. It's very much on a case-by-case basis, but in terms of stability, in terms of mobilization, the parameters that we're engineering for bound or unbound enzymes can be quite similar. So the process, like Tim says, can if that's the objective that you're trying to engineer, then that can be factored in as you do it. But the core bit of the technology isn't around immobilization.
Perfect. Thanks very much. And yeah, I encourage you to follow up afterwards. And Chris, I think, has said thank you in the chat. A question from Rory about what expression hosts have you looked at? And do you have any models that look at enzyme activity in vivo?
Yeah, they're quite connected, those two. So we very much focus the actual engineering lab process around your conventional E. coli expression systems. Two reasons. One, it's the most amenable for our workflows in terms of rapidly growing and expressing. So making actually the enzyme prototype, if you like, the variant, and screening that. There's the most tools available using E. coli, but it's also the most used that our customers are looking at as well. So it's the most kind of industrially and commercially relevant strain that people are using. So it makes sense for us, if we're going to find a hit, it has to be compatible in the expression system that customers are wanting, and they're all wanting it in E. coli. So so there obviously are many more, and it might be something in the future that we look to expand. There's plenty of interest in terms of cell-free, and that also works pretty well. But we find that if we can optimize an enzyme in E. coli, which is the customer's go-to strain, then those improvements are most transferable from our lab into the customer's lab. So yeah, focus on E. coli really, because that's what industry are primarily wanting at the moment.
I think that's a key. Sorry, just to add, a key learning from commercialization of an early stage technology is you've got to find out what you're initially quite good at. You can't do everything, basically, so we can't, basically try lots of different industrial strains or try too many things at once. You have to sort of quite quickly focus on your sort of beachhead market and where your technology fits the best. Go there, validate it, and then you begin off the back of that success, you can begin to expand out and try and test different technology improvements, as we are, doing. Andy's already mentioned sort of things like cell-free technology, other things. So there's, plenty of cool things we'll be doing in the future.
Brilliant, thank you. And I'll just take one last question from Zach. To what extent can you involve multiple processes in enzyme simultaneously? So can you look at the stability, activity, selectivity?
Yeah, I really like that question. Given time, I've not really gone into it much, but that's exactly what we are doing with our approach. So if you could picture the scheme of the various inputs into our AI-guided design step, that kind of schematic where we had molecular modeling, protein large language models, and the structural predictions. That's kind of like a high-level view. There's actually about 7 different algorithms that we use, all modeling and predicting different properties of the enzyme that we're looking at. So these are very specific predictions based on the enzyme in question. They are looking at different properties of that enzyme. So the modeling is looking at stabilizing the transition state and actually trying to get an improved catalysis and yield. We are modeling as well in the other algorithm stability, and some of the more structural based ones are looking at selectivity. So we are generating those predictions on different properties. All of those feed into the model for the AI. And actually, one of the amazing things of what AI can do, it can take these multiple inputs, consider them, and we use that model to generate predictions that are optimal at more than one property. So we actually we query the model to generate predictions for an experiment for variants that are better, not just in yield, but in stability and So we want variants that are not just better turning over the substrate, but are also stable. Very often mutations are destabilizing, so you might have a better enzyme if you purify it, has a better K-cat, but if you've got a fraction of the expression, that's not an enzyme that is going to go forward to commercial scale up. So yeah, we are doing kind of multi-parameter optimization within the platform, and those predictions are multi-parameter predictions. So yeah, I'm glad you asked that. It wasn't something I had much time to go into, but yeah, that's absolutely something we're doing.
That's perfect. Thank you very much. And it was a great question to end on, I think. And then there's a few others that have come into the chat, one asking you about partnering or potentially partnering or looking for partners for open call for the European projects. But I noticed you put your email in there, Tim, so people can follow up with you guys afterwards. And you can answer the chat. I'm sure you'll have access to it. Just want to finish off by saying thank you very much to Tim and Andy, and also thank you very much to everybody who has joined us today. And we will have our next webinar in a month's time, and I've forgotten to look up when they are and where it is. Jennifer is going to tell me off, but we'll pop it in there she goes, she's popped the events calendar in. So we've got a few other webinars lined up for the next couple of months, but also a call out if anybody who's on the call and does want to give a webinar, wants to share their results, share and ask to the wider community, please drop a message into the chat here and or email ibic@manchester.ac.uk. Brilliant. Thank you very much, everybody. Lovely to see you again, Tim, Andy. I'm sure we'll catch up soon. And have a good afternoon, everybody. Thanks very much.
Thank you, everyone.
Thank you.
Bye. Bye.
Bye.